The Fourier transform, named after Joseph Fourier, is a mathematical transformation employed to transform signals between time domain and frequency domain, which has many applications in physics and engineering. It is reversible, being able to transform from either domain to the other. The term itself refers to both the transform operation and to the function it produces. In the case of a periodic function over time, the Fourier transform can be simplified to the calculation of a discrete set of complex amplitudes, called Fourier series coefficients. They represent the frequency spectrum of the original time domain signal. Also, when a time domain function is sampled to facilitate storage or computer processing, it is still possible to recreate a version of the original Fourier transform according to the Poisson summation formula, also known as discrete-time Fourier transform. See also Fourier analysis and list of Fourier-related transforms. Definition: there are several common conventions for defining the Fourier transform of an integrable function. This article will use the following definition: for any real number i3/4. When the independent variable x represents time, the transform variable i3/4 represents frequency. Under suitable conditions, is determined by via the inverse transform, for any real number x. The statement that can be reconstructed from is known as the Fourier Inversion theorem, and was first introduced in Fourier's analytical theory of heat, although what would be considered a proof by modern standards was not given until much later. The functions and often are referred to as a Fourier integral pair or Fourier transform pair. For other common conventions and notations, including using the angular frequency I per mil instead of the frequency i3/4, see other conventions and other notations below. The Fourier transform on Euclidean space is treated separately, in which the variable x often represents position and i3/4 momentum. Introduction. The motivation for the Fourier transform comes from the study of Fourier series. In the study of Fourier series, complicated but periodic functions are written as the sum of simple waves mathematically represented by sines and cosines. The Fourier transform is an extension of the Fourier series that results when the period of the represented function is lengthened and allowed to approach infinity. Due to the properties of sine and cosine, it is possible to recover the amplitude of each wave in a Fourier series using an integral. In many cases it is desirable to use Euler's formula, which states that e2i equals cos 2i plus I sin 2i, to write Fourier series in terms of the basic waves e2i. This has the advantage of simplifying many of the formulas involved, and provides a formulation for Fourier series that more closely resembles the definition followed in this article. Rewriting sines and cosines as complex exponentials makes it necessary for the Fourier coefficients to be complex valued. The usual interpretation of this complex number is that it gives both the amplitude of the wave present in the function and the phase of the wave. These complex exponentials sometimes contain negative frequencies. If I is measured in seconds, then the waves e2i and a2i both complete one cycle per second, but they represent different frequencies in the Fourier transform. Hence, frequency no longer measures the number of cycles per unit time, but is still closely related. There is a close connection between the definition of Fourier series and the Fourier transform for functions f which are zero outside of an interval. For such a function, we can calculate its Fourier series on any interval that includes the points where f is not identically zero. The Fourier transform is also defined for such a function. As we increase the length of the interval on which we calculate the Fourier series, then the Fourier series coefficients begin to look like the Fourier transform and the sum of the Fourier series of f begins to look like the inverse Fourier transform. To explain this more precisely, suppose that t is large enough so that the interval, a t2, contains the interval on which f is not identically zero. Then the nth series coefficient Cn is given by. Comparing this to the definition of the Fourier transform, it follows that since f, x, is zero outside, a t2. Thus the Fourier coefficient suggests the values of the Fourier transform sampled on a grid of width 1 per ton, multiplied by the grid width 1 per ton. Under appropriate conditions, the Fourier series of f will equal the function f. In other words, f can be written where the last sum is simply the first sum rewritten using the definitions I3/4 n equals nt, and I3/4 equals /tant equals 1 per ton. This second sum is a Riemann sum, and so by letting ta it will converge to the integral for the inverse Fourier transform given in the definition section. Under suitable conditions this argument may be made precise. In the study of Fourier series the numbers Cn could be thought of as the amount of the wave present in the Fourier series of f. Similarly, as seen above, the Fourier transform can be thought of as a function that measures how much of each individual frequency is present in our function f, and we can recombine these waves by using an integral to reproduce the original function. Example: the following images provide a visual illustration of how the Fourier transform measures whether a frequency is present in a particular function. The function depicted f, t, equals cos, 6 I euro t, a I euro t2 oscillates at 3 Hz and tends quickly to 0. This function was specially chosen to have a real Fourier transform which can easily be plotted. The first image contains its graph. In order to calculate we must integrate a to I euro I. 3t, f, t. The second image shows the plot of the real and imaginary parts of this function. The real part of the integrand is almost always positive, because when f, t, is negative, the real part of a to I euro I, 3t, is negative as well. Because they oscillate at the same rate, when f, t, is positive, so is the real part of a to I euro I, 3t. The result is that when you integrate the real part of the integrand you get a relatively large number. On the other hand, when you try to measure a frequency that is not present, as in the case when we look at, the integrand oscillates enough so that the integral is very small. The general situation may be a bit more complicated than this, but this in spirit is how the Fourier transform measures how much of an individual frequency is present in a function f, t. Properties of the Fourier transform. Here we assume f, x, g, x, and h, x, are integrable functions, are Lebesgue measurable on the real line, and satisfy. We denote the Fourier transforms of these functions by a euro and a euro respectively. Basic properties: the Fourier transform has the following basic properties. Linearity: for any complex numbers a and b, if h, x, equals half, x, plus bg, x, then a euro. Translation: for any real number xo, if a euro then a euro. Modulation: for any real number I3/4 0 if then a euro. Scaling: for a non-zero real number a, if h, x, equals f, ax, then a euro aaa. The case a equals a 1 leads to the time reversal property, which states, if h, x, equals f, ax, then, conjugation. If a euro then a euro. In particular, if f is real, then one has the reality condition a euro, that is a Hermitian function. And if f is purely imaginary, then a euro. Integration, substituting in the definition, we obtain. That is, the evaluation of the Fourier transform in the origin equals the integral of f all over its domain. Invertibility and periodicity. Under suitable conditions on the function f, it can be recovered from its Fourier transform indeed, denoting the Fourier transform operator by so then for suitable functions, applying the Fourier transform twice simply flips the function, which can be interpreted as reversing time. Since reversing time is too periodic, applying this twice yields so the Fourier transform operator is 4 periodic, and similarly the inverse Fourier transform can be obtained by applying the Fourier transform 3 times, in particular the Fourier transform is invertible. More precisely, defining the parity operator that inverts time. These equalities of operators require careful definition of the space of functions in question, defining equality of functions and defining equality of operators a euro, that is, defining the topology on the function space and operator space in question. These are not true for all functions, but are true under various conditions, which are the content of the various forms of the Fourier inversion theorem. This fourfold periodicity of the Fourier transform is similar to a rotation of the plane by 90 degrees, particularly as the two-fold iteration yields a reversal, and in fact this analogy can be made precise. While the Fourier transform can simply be interpreted as switching the time domain and the frequency domain, with the inverse Fourier transform switching them back, more geometrically it can be interpreted as a rotation by 90 degree in the time frequency domain, and the Fourier transform can be generalized to the fractional Fourier transform, which involves rotations by other angles. This can be further generalized to linear canonical transformations, which can be visualized as the action of the special linear group SL2, R, on the time frequency plane, with the preserved symplectic form corresponding to the uncertainty principle, below. This approach is particularly studied in signal processing, under time frequency analysis. Uniform continuity and the Riemann-Leibniz lemma. The Fourier transform may be defined in some cases for non-integrable functions, but the Fourier transforms of integrable functions have several strong properties. The Fourier transform of any integrable function f is uniformly continuous and, by the Riemann-Leibniz lemma, however, need not be integrable. For example, the Fourier transform of the rectangular function, which is integrable, is the sinc function, which is not Leibniz integrable, because its improper integrals behave analogously to the alternating harmonic series, in converging to a sum without being absolutely convergent. It is not generally possible to write the inverse transform as a Leibniz integral. However, when both f and r are integrable, the inverse equality holds almost everywhere. That is, the Fourier transform is injective on L1, R. Plancherel theorem and Parseval's theorem, let f, x, and g, x, be integrable, and let n be their Fourier transforms. If f, x, and g, x, are also square integrable, then we have Parseval's theorem, where the bar denotes complex conjugation. The Plancherel theorem, which is equivalent to Parseval's theorem, states: the Plancherel theorem makes it possible to extend the Fourier transform, by a continuity argument, to a unitary operator on L2, R. On L1, R, a copyright L2, R, this extension agrees with original Fourier transform defined on L1, R, thus enlarging the domain of the Fourier transform to L1, R, plus L2, R, for 1 a Permel currency P a Permel 2 currency. The Plancherel theorem has the interpretation in the sciences that the Fourier transform preserves the energy of the original quantity. Depending on the author, either of these theorems might be referred to as the Plancherel theorem or as Parseval's theorem. See Pontryagin duality for a general formulation of this concept in the context of locally compact abelian groups. Poisson summation formula. The Poisson summation formula is an equation that relates the Fourier series coefficients of the periodic summation of a function to values of the function's continuous Fourier transform. It has a variety of useful forms that are derived from the basic one by application of the Fourier transform's scaling and time-shifting properties. The frequency domain dual of the standard PSF is also called discrete-time Fourier transform, which leads directly to a popular, graphical, frequency domain representation of the phenomenon of aliasing, and a proof of the Nyquist-Shannon sampling theorem. Convolution theorem. The Fourier transform translates between convolution and multiplication of functions. If f, x, and g, x, are integrable functions with Fourier transforms and respectively, then the Fourier transform of the convolution is given by the product of the Fourier transforms and. This means that if where a denotes the convolution operation, then in linear time invariant system theory, it is common to interpret g, x, as the impulse response of an LTI system with input f, x, and output h, x, since substituting the unit impulse for f, x, yields h, x, equals g, x. In this case, represents the frequency response of the system. Conversely, if f, x, can be decomposed as the product of two square integrable functions p, x, and q, x, then the Fourier transform of f, x, is given by the convolution of the respective Fourier transforms and cross-correlation theorem. In an analogous manner, it can be shown that if H, x, is the cross-correlation of f, x, and g, x, then the Fourier transform of H, x, is. As a special case, the autocorrelation of function f, x, is. For which eigenfunctions, one important choice of an orthonormal basis for L2, R, is given by the Hermite functions, where hen, x, are the probabilist's Hermite polynomials, defined by. Under this convention for the Fourier transform, we have that. In other words, the Hermite functions form a complete orthonormal system of eigenfunctions for the Fourier transform on L2, R. However, this choice of eigenfunctions is not unique. There are only 4 different eigenvalues of the Fourier transform, and any linear combination of eigenfunctions with the same eigenvalue gives another eigenfunction. As a consequence of this, it is possible to decompose L2, R, as a direct sum of 4 spaces HO, H1, H2, and H3 where the Fourier transform acts on Hec simply by multiplication by IC. Since the complete set of Hermite functions provides a resolution of the identity, the Fourier transform can be represented by such a sum of terms weighted by the above eigenvalues, and these sums can be explicitly summed. This approach to define the Fourier transform was first done by Norbert Wiener, Duo and Ikoichi 2001. Among other properties, Hermite functions decrease exponentially fast in both frequency and time domains, and they are thus used to define a generalization of the Fourier transform, namely the fractional Fourier transform used in time-frequency analysis. In physics, this transform was introduced by Edward Condorner, Cond in 1937. Fourier transform on Euclidean space. The Fourier transform can be defined in any arbitrary number of dimensions n. As with the one-dimensional case, there are many conventions. For an integrable function f, x, this article takes the definition where x and I3/4 are n-dimensional vectors, and zao a I3/4 is the dot product of the vectors. The dot product is sometimes written as. All of the basic properties listed above hold for the n-dimensional Fourier transform, as do Plancherel's and Parseval's theorem. When the function is integrable, the Fourier transform is still uniformly continuous and the Riemann-Leibniz lemma holds. Uncertainty principle. Generally speaking, the more concentrated f, x, is, the more spread out its Fourier transform must be. In particular, the scaling property of the Fourier transform may be seen as saying, if we squeeze a function in x, its Fourier transform stretches out in I3/4. It is not possible to arbitrarily concentrate both a function and its Fourier transform. The trade-off between the compaction of a function and its Fourier transform can be formalized in the form of an uncertainty principle by viewing a function and its Fourier transform as conjugate variables with respect to the symplectic form on the Tamiya frequency domain. From the point of view of the linear canonical transformation, the Fourier transform is rotation by 90 a degree in the Tamiya frequency domain, and preserves the symplectic form. Suppose f, x, is an integrable and square integrable function. Without loss of generality, assume that f, x, is normalized. It follows from the Plancherel theorem that is also normalized. The spread around z equals 0 may be measured by the dispersion about 0 defined by. In probability terms, this is the second moment of f, x, to about 0. The uncertainty principle states that, if f, x, is absolutely continuous and the functions a f, x, and phi squared, x, are square integrable, then, a Pinsky 2002. The equality is attained only in the case where I florin 0 is arbitrary and so that f is L2 a normalized. In other words, where f is a Gaussian function with variance I2 florins, centered at 0, and its Fourier transform is a Gaussian function with variance I florin A2. In fact, this inequality implies that for any xo, I3/4 0 are R. In quantum mechanics, the momentum and position wave functions are Fourier transform pairs, to within a factor of Planck's constant. With this constant properly taken into account, the inequality above becomes the statement of the Heisenberg uncertainty principle. A stronger uncertainty principle is the Hirshman uncertainty principle, which is expressed as where h, p, is the differential entropy of the probability density function p, x, where the logarithms may be in any base which is consistent. The equality is attained for a Gaussian, as in the previous case. Spherical harmonics. Let the set of homogeneous harmonic polynomials of degree k on Rn be denoted by arc. The set arc consists of the solid spherical harmonics of degree k. The solid spherical harmonics play a similar role in higher dimensions to the Hermite polynomials in dimension 1. Specifically, if f, x, equals ai euro x to p, x, for some p, x, in arc, then let the set hk be the closure in L2, Rn, of linear combinations of functions of the form f, x p, x, where p, x, is in arc. The space L2, Rn, is then a direct sum of the spaces hk, and the Fourier transform maps each space hk to itself and is possible to characterize the action of the Fourier transform on each space hk. Let f, x, equals fo, xp, x, in arc, then where. Here j, na plus a do ka a2, /2 denotes the Bessel function of the first kind with order /2. When chi equals a0, this gives a useful formula for the Fourier transform of a radial function. Note that this is essentially the Hankel transform. Moreover, there is a simple recursion relating the cases n plus 2 and n, allowing to compute, for example, the three-dimensional Fourier transform of a radial function from the one-dimensional one. Restriction problems. In higher dimensions it becomes interesting to study restriction problems for the Fourier transform. The Fourier transform of an integrable function is continuous and the restriction of this function to any set is defined. But for a square integrable function the Fourier transform could be a general class of square integrable functions. As such, the restriction of the Fourier transform of an L2, Rn, function cannot be defined on sets of measure 0. It is still an active area of study to understand restriction problems in LP for 1AA par 2. Surprisingly, it is possible in some cases to define the restriction of a Fourier transform to a set S, provided S has non-zero curvature. The case when S is the unit sphere in Rn is of particular interest. In this case the Thomas-Stein restriction theorem states that the restriction of the Fourier transform to the unit sphere in Rn is a bounded operator on LP provided 1 a per mil currency pa per mil euro/a euro, n plus 3. One notable difference between the Fourier transform in one dimension versus higher dimensions concerns the partial sum operator. Consider an increasing collection of measurable sets E are indexed by Ra 0, such as balls of radius are centered at the origin, or cubes of side 2r. For a given integrable function f, consider the function f are defined by. Suppose in addition that f are Lp, Rn. For n equals 1 and 1, p, a, if one takes er equals, then f converges to f in Lp as a tends to infinity, by the boundedness of the Hilbert transform. Naively one may hope the same holds true for n greater than 1. In the case that er is taken to be a cube with side length r, then convergence still holds. Another natural candidate is the Euclidean ball era equals I3/4 aa I3/4 r. In order for this partial sum operator to converge, it is necessary that the multiplier for the unit ball be bounded in Lp, Rn. For Na per mil beta 2 it is a celebrated theorem of Charles Furman that the multiplier for the unit ball is never bounded unless par equals A2. In fact, when Pa per mil 2, this shows that not only may Fr fail to converge to f in Lp, but for some functions f in Lp, Rn, Fr is not even an element of Lp. Fourier transform on function spaces, on Lp spaces, on L1, the definition of the Fourier transform by the integral formula is valid for Liebsche integrable functions f. That is, f for L1, Rn. The Fourier transform, L1, Rn, Euler, Rn, is a bounded operator. This follows from the observation that which shows that its operator norm is bounded by 1. Indeed it equals 1, which can be seen, for example, from the transform of the rect function. The image of L1 is a subset of the space CO, Rn, of continuous functions that tend to zero at infinity, although it is not the entire space. Indeed, there is no simple characterization of the image. On L2, since compactly supported smooth functions are integrable and dense in L2, Rn, the Plancherel theorem allows us to extend the definition of the Fourier transform to general functions in L2, Rn, by continuity arguments. The Fourier transform in L2, Rn, is no longer given by an ordinary Lebesgue integral, although it can be computed by an improper integral, here meaning that for an L2 function f, where the limit is taken in the L2 sense. Many of the properties of the Fourier transform in L1 carry over to L2, by a suitable limiting argument. Furthermore, L2, Rn, L2, Rn, is a unitary operator. For an operator to be unitary it is sufficient to show that it is bijective and preserves the inner product, so in this case these follow from the Fourier inversion theorem combined with the fact that for any f, GAU L2, Rn, we have. In particular, the image of L2, Rn, is itself under the Fourier transform. On other LP, the definition of the Fourier transform can be extended to functions in LP, Rn, for 1 a per mole currency p a per mole 2 currency by decomposing such functions into a fat tail part in L2 plus a fat body part in L1. In each of these spaces, the Fourier transform of a function in LP, Rn, is in LQ, Rn, whereas the Haar paragraph LDE a conjugate of p by the Hausdorff-Euro-Young inequality. However, except for p equals 2, the image is not easily characterized. Further extensions become more technical. The Fourier transform of functions in LP for the range 2, p, a requires the study of distributions. In fact, it can be shown that there are functions in LP with p greater than 2 so that the Fourier transform is not defined as a function. Tempered distributions. One might consider enlarging the domain of the Fourier transform from L1 plus L2 by considering generalized functions, or distributions. A distribution on Rn is a continuous linear functional on the space Cc, Rn, of compactly supported smooth functions, equipped with a suitable topology. The strategy is then to consider the action of the Fourier transform on Cc, Rn, and pass to distributions by duality. The obstruction to do this is that the Fourier transform does not map Cc, Rn, to Cc, Rn. In fact the Fourier transform of an element in Cc, Rn, cannot vanish on an open set. See the above discussion on the uncertainty principle. The right space here is the slightly larger space of Schwarz functions. The Fourier transform is an automorphism on the Schwarz space, as a topological vector space, and thus induces an automorphism on its dual, the space of tempered distributions, Stein and Weiss 1971. The tempered distribution include all the integrable functions mentioned above, as well as well-behaved functions of polynomial growth and distributions of compact support. For the definition of the Fourier transform of a tempered distribution, let f and g be integrable functions, and let n be their Fourier transforms respectively. Then the Fourier transform obeys the following multiplication formula. Every integrable function f defines a distribution Tf by the relation AAA for all Schwarz functions I. So it makes sense to define Fourier transform of Tf by for all Schwarz functions I. Extending this to all tempered distributions T gives the general definition of the Fourier transform. Distributions can be differentiated and the above-mentioned compatibility of the Fourier transform with differentiation and convolution remains true for tempered distributions. Generalizations, Fourier-Euroschild transform, the Fourier transform of a finite Borel measure I1/4 on Rn is given by. This transform continues to enjoy many of the properties of the Fourier transform of integrable functions. One notable difference is that the Riemann-Euro-Lebesgue lemma fails for measures. In the case that d1/4 equals f, x, dx, then the formula above reduces to the usual definition for the Fourier transform of f. In the case that I1/4 is the probability distribution associated to a random variable x, the Fourier-Schultes transform is closely related to the characteristic function, but the typical conventions in probability theory take ax and I3/4 instead of a2i x and I3/4. In the case when the distribution has a probability density function, this definition reduces to the Fourier transform applied to the probability density function, again with a different choice of constants. The Fourier transform may be used to give a characterization of measures. Bochner's theorem characterizes which functions may arise as the Fourier-Schultes transform of a positive measure on the circle. Furthermore, the Dirac delta function is not a function but it is a finite Borel measure. Its Fourier transform is a constant function. Locally compact abelian groups. The Fourier transform may be generalized to any locally compact abelian group. A locally compact abelian group is an abelian group which is at the same time a locally compact Hausdorff topological space so that the group operation is continuous. If G is a locally compact abelian group, it has a translation invariant measure I1/4, called Haar measure. For a locally compact abelian group G, the set of irreducible, that is one-dimensional, unitary representations are called its characters. With its natural group structure and the topology of pointwise convergence, the set of characters is itself a locally compact abelian group, called the Pontryagin dual of G. For a function f in L1, G, its Fourier transform is defined by. The Riemann-Leibniz lemma holds in this case. Is a function vanishing at infinity on Gelfand transform. The Fourier transform is also a special case of Gelfand transform. In this particular context, it is closely related to the Pontryagin duality map defined above. Given an abelian locally compact Hausdorff topological group G, as before we consider space L1, G, defined using a Haar measure. With convolution as multiplication, L1, G, is an abelian Banach algebra. It also has an involution given by. Taking the completion with respect to the largest possibly C norm gives its enveloping C algebra, called the group C algebra C, G, of G is bounded by the L1 norm, therefore their supremum exists. Given any abelian C algebra A, the Gelfand transform gives an isomorphism between A and CO, where A is the multiplicative linear functionals, that is one-dimensional representations, on A with the weak topology. The map is simply given by. It turns out that the multiplicative linear functionals of C, G, after suitable identification, are exactly the characters of G, and the Gelfand transform, when restricted to the dense subset L1, G, is the Fourier-Pontryagin transform. Non-abelian groups. The Fourier transform can also be defined for functions on a non-abelian group, provided that the group is compact. Removing the assumption that the underlying group is abelian, irreducible unitary representations need not always be one-dimensional. This means the Fourier transform on a non-abelian group takes values as Hilbert space operators. The Fourier transform on compact groups is a major tool in representation theory and non-commutative harmonic analysis. Let G be a compact Hausdorff topological group. Let I denote the collection of all isomorphism classes of finite-dimensional irreducible unitary representations, along with a definite choice of representation U, I florin on the Hilbert space high florin of finite dimension D florin for each I florin A I. If I1/4 is a finite Borel measure on G, then the Fourier-Schultes transform of I1/4 is the operator on high florin defined by. Where is the complex conjugate representation of U, I florin acting on high florin? If I1/4 is absolutely continuous with respect to the left invariant probability measure I on G, represented as. For some f for L1, I, one identifies the Fourier transform of f with the Fourier-Schultes transform of I1/4. The mapping defines an isomorphism between the Banach space M, G, a finite Borel measures and a closed subspace of the Banach space K, I consisting of all sequences E equals indexed by I of linear operators early florin high florin a high florin for which the norm is finite. The convolution theorem asserts that, furthermore, This isomorphism of Banach spaces is in fact an isometric isomorphism of C algebras into a subspace of car, a pound. Multiplication on M, G, is given by convolution of measures and the involution defined by and car, a pound has a natural C algebra structure as Hilbert space operators. The Plancherel theorem holds, and a version of the Fourier inversion formula follows, if F(L2, G, then where the summation is understood as convergent in the L2 sense. The generalization of the Fourier transform to the non-commutative situation has also in part contributed to the development of non-commutative geometry. In this context, a categorical generalization of the Fourier transform to non-commutative groups is Tanmakar-Eurocrin duality, which replaces the group of characters with the category of representations. However, this loses the connection with harmonic functions. Alternatives, in signal processing terms, a function is a representation of a signal with perfect time resolution, but no frequency information, while the Fourier transform has perfect frequency resolution, but no time information. The magnitude of the Fourier transform at a point is how much frequency content there is, but location is only given by phase, and standing waves are not localized in time. A sine wave continues out to infinity, without decaying. This limits the usefulness of the Fourier transform for analyzing signals that are localized in time, notably transients, or any signal of finite extent. As alternatives to the Fourier transform, in time-frequency analysis, one uses time-frequency transforms or time-frequency distributions to represent signals in a form that has some time information and some frequency information. By the uncertainty principle, there is a trade-off between these. These can be generalizations of the Fourier transform, such as the short-time Fourier transform or fractional Fourier transform, or other functions to represent signals, as in wavelet transforms and chirplet transforms, with the wavelet analog of the Fourier transform being the continuous wavelet transform. Applications: analysis of differential equations. Fourier transforms and the closely related Laplace transforms are widely used in solving differential equations. The Fourier transform is compatible with differentiation in the following sense: if f, x, is a differentiable function with Fourier transform, then the Fourier transform of its derivative is given by. This can be used to transform differential equations into algebraic equations. This technique only applies to problems whose domain is the whole set of real numbers. By extending the Fourier transform to functions of several variables, partial differential equations with domain Rn can also be translated into algebraic equations. Fourier transform spectroscopy. The Fourier transform is also used in nuclear magnetic resonance and in other kinds of spectroscopy, for example infrared. In NMR, an exponentially shaped free induction decay signal is acquired in the time domain and Fourier transformed to a Lorentzian line shape in the frequency domain. The Fourier transform is also used in magnetic resonance imaging and mass spectrometry. Quantum mechanics and signal processing. In quantum mechanics, Fourier transforms of solutions to the Schrödinger equation are known as momentum space wave functions. They display the amplitudes for momenta. Their absolute square is the probabilities of momenta. This is valid also for classical waves treated in signal processing, such as in swept frequency radar where data is taken in frequency domain and transformed to time domain, yielding range. The absolute square is then the power. Other common notations for include denoting the Fourier transform by a capital letter corresponding to the letter of function being transformed, and f(I3/4) is especially common in the sciences and engineering. In electronics, the omega is often used instead of I3/4 due to its interpretation as angular frequency. Sometimes it is written as f(G) per mil, where J is the imaginary unit, to indicate its relationship with the Laplace transform, and sometimes it is written informally as f(2I)f, in order to use ordinary frequency. The interpretation of a complex function may be aided by expressing it in polar coordinate form. In terms of the two real functions I3/4 and I3/4, where is the amplitude and is the phase. then the inverse transform can be written, which is a recombination of all the frequency components of f, x. Each component is a complex sinusoid of the form e2i xi 3/4 whose amplitude is a, I 3/4 and whose initial phase angle is I 3/4. The Fourier transform may be thought of as a mapping on function spaces. This mapping is here denoted and is used to denote the Fourier transform of the function f. This mapping is linear, which means that can also be seen as a linear transformation on the function space and implies that the standard notation in linear algebra of applying a linear transformation to a vector can be used to write instead of. Since the result of applying the Fourier transform is again a function, we can be interested in the value of this function evaluated at the value I 3/4 for its variable, and this is denoted either as or as. Notice that in the former case, it is implicitly understood that is applied first to f and then the resulting function is evaluated at I 3/4, not the other way around. In mathematics and various applied sciences, it is often necessary to distinguish between a function f and the value of f when its variable equals x, denoted f, x. This means that a notation like formally can be interpreted as the Fourier transform of the values of f at x. Despite this flaw, the previous notation appears frequently, often when a particular function or a function of a particular variable is to be transformed. For example, is sometimes used to express that the Fourier transform of a rectangular function is a sinc function, or is used to express the shift property of the Fourier transform. Notice that the last example is only correct under the assumption that the transformed function is a function of x, not of xo. Other conventions. The Fourier transform can also be written in terms of angular frequency, I per mil equals 2i I 3/4 whose units are radians per second. The substitution I 3/4 equals I per mil / 2i into the formulas above produces this convention. Under this convention, the inverse transform becomes. Unlike the convention followed in this article, when the Fourier transform is defined this way, it is no longer a unitary transformation on L2, Rn. There is also less symmetry between the formulas for the Fourier transform and its inverse. Another convention is to split the factor OFN evenly between the Fourier transform and its inverse, which leads to definitions. Under this convention, the Fourier transform is again a unitary transformation on L2, Rn. It also restores the symmetry between the Fourier transform and its inverse. Variations of all three conventions can be created by conjugating the complex exponential kernel of both the forward and the reverse transform. The signs must be opposites. Other than that, the choice is a matter of convention. As discussed above, the characteristic function of a random variable is the same as the Fourier-Schiltjes transform of its distribution measure, but in this context it is typical to take a different convention for the constants. Typically characteristic function is defined. As in the case of the non-unitary angular frequency convention above, there is no factor of 2i appearing in either of the integral, or in the exponential. Unlike any of the conventions appearing above, this convention takes the opposite sign in the exponential. Tables of important Fourier transforms. The following tables record some closed-form Fourier transforms. For functions f, x, g, x, and h, x, denote their Fourier transforms by, and respectively. Only the three most common conventions are included. It may be useful to notice that entry 105 gives a relationship between the Fourier transform of a function and the original function, which can be seen as relating the Fourier transform and its inverse. Functional relationships. The Fourier transforms in this table may be found in Erda copyright Lai or Kamler. Square integrable functions. The Fourier transforms in this table may be found in or the appendix of. Distributions. The Fourier transforms in this table may be found in or the appendix of. Two-dimensional functions. Remarks. To 400, the variables I 3/4 x, I 3/4 y, I per mil x, I per mil y, I 1/2 x and I 1/2 y are real numbers. The integrals are taken over the entire plane. To 401, both functions are Gaussians, which may not have unit volume. To 402, the function is defined by sec r, equals 1 0 a per mil currency ra per mil 1 currency, and a 0 otherwise. This is the Airy distribution, and is expressed using J1. Formulas for general n-dimensional functions. Remarks. To 501, the function I, 0, 1, is the indicator function of the interval, 0, 1. The function I, x, is the gamma function. The function Jn/2 plus I is a Bessel function of the first kind, with order n/2 plus I. Taking n equals 2 and I equals 0 produces 402. To 502, see Rice potential. The formula also holds for all I plus or minus a per mil an a1, a euro by analytic continuation, but then the function and its Fourier transforms need to be understood as suitably regularized tempered distributions. See homogeneous distribution. To 503, this is the formula for a multivariate normal distribution normalized to 1 with a mean of 0. Bold variables are vectors or matrices. Following the notation of the aforementioned page, and, to 504, here. See also. References, Borchach, B., ed., Time Frequency Signal Analysis and Processing, a Comprehensive Reference, Oxford, Elsevier Science, ISBN A0-08-044335-4, Bochner S., Chandrasekhar K., Fourier Transforms, Princeton University Press, Fractional, R.N., The Fourier Transform and Its Applications, Boston, McGraw-Hill, ISBN A0-07-116043-4A. Campbell, George. Foster, Ronald, Fourier Integrals for Practical Applications, New York, D. Van Nostrand Company, Incorporated A. Condon, E.U., Immersion of the Fourier Transform in a Continuous Group of Functional Transformations, Proc. Nat. Ackerd. Sci. USA 23, 158 euro 164a. Duo and Ikoichi, Javier, Fourier Analysis, American Mathematical Society, ISBN A0-8218-2172-5A. Dim, H. McKean, H., Fourier Series and Integrals, Academic Press, ISBN A978-0-12-226451-1A. Erda Copyright Lai, Arthur, ed., Tables of Integral Transforms 1, New York, McGraw-Hill, Fourier, J. B. Joseph, Thar Copyright Array Analytique de la Chaleur, Paris, Chez Firmin Didot, Paris Filsa, Fourier, J. B. Joseph. Freeman, Alexander, Translator, The Analytical Theory of Heat, The University Press, Graph Echoes, Laucas, Classical and Modern Fourier Analysis, Prentice Hall, ISBN A0-13-035399 ZAM. Graph Echoes, Laucas. Teschl, Gerald, On Fourier Transforms of Radial Functions and Distributions, J. Fourier Anal. APPL 19, 167 €179, doi, 10.1007 per second 00041-012-9242-5A. Hewitt, Edwin. Ross, Kenneth A., Abstract Harmonic Analysis. Vol. 2, Structure and Analysis for Compact Groups. Analysis on locally compact abelian groups, Diagran de Leer and Der Mathematician was Senschaffen, Band 152, Berlin, New York, Springer Verlag, MRO 2627773A. Haar paragraph Ramander, L., Linear Partial Differential Operators, Volume 1, Springer Verlag, ISBN A978-3-540-00662-6A. James, J.F., A Student's Guide to Fourier Transforms, New York, Cambridge University Press, ISBN A978-0-521-17683-5A. Kaiser, Gerald, A Friendly Guide to Wavelets, Berger Currency User, ISBN A0-8176-3711-7A. Kamler, David, A First Course in Fourier Analysis, Prentice Hall, ISBN A0-13-578782-3. Carl-Elson, Yitzhak, An Introduction to Harmonic Analysis, Dover, ISBN A0-486-63331-4. Knapp, Anthony W., Representation Theory of Semisimple Groups, An Overview Based on Examples, Princeton University Press, ISBN A978-0-691-09089-4. Pinsky, Mark, Introduction to Fourier Analysis and Wavelets, Brooks Cole, ISBN A0-533-37660-6. Polyanin, A.D. Manzarov, A.V., Handbook of Integral Equations, Boca Raton, CRC Press, ISBN A0-8493-2876-4A. Rudin, Walter, Real and Complex Analysis, Singapore, McGraw-Hill, ISBN A0-07-100276-6A. Rahman, Meisha, Applications of Fourier Transforms to Generalized Functions, WIT Press, ISBN A1845645,642A. Stein, Elias. Shakarchai, Rami, Fourier Analysis, An Introduction, Princeton University Press, ISBN A0-691-11384. Zam. Stein, Elias. Weiss, Guido, Introduction to Fourier Analysis on Euclidean Spaces, Princeton, New Jersey. Princeton University Press, ISBN A978-691-08078-9A. Taneja, H.C., Chapter 18, Fourier Integrals and Fourier Transforms, Advanced Engineering Mathematics, Volume 2, New Delhi, India, IK International Private Ltd., ISBN A8189866,567A. Titchmarsh, E., Introduction to the Theory of Fourier Integrals, Oxford University, Clarendon Press, ISBN A978-0-8284-0324-5A. Wilson, A.G., Fourier Series and Optical Transform Techniques in Contemporary Optics, New York, Wiley, ISBN A0-471-30357-7A. Yoster, K., Functional Analysis, Springer Verlag, ISBN A3-540-58654-7A. External links, The Discrete Fourier Transformation, Definition and Numerical Examples, a MATLAB tutorial, the Fourier Transform tutorial site, Fourier Series Applet. Stefan Bernsies FFTLAB, Stanford Video Course on the Fourier Transform, Haswinkel, Michiel, ed., Fourier Transform, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Wellerstein, Eric W., Fourier Transform, MathWorld. The DFT Oiapeda Mastering the Fourier Transform in 1 Day at the DSP Dimension, an interactive flash tutorial for the Fourier Transform, Java library for DFT, Fourier Transforms. Gary D. Knott, Fourier Transforms on www.continuummechanics.org.